Okay, so today we're going to review some of the things that we learned in grade 11 with respect to solutions and take that into our grade 12 level course. We're going to see a lot of applications of solutions, solubility, dissociation, and those kinds of things in this course. So just a quick review. We've got to remember the different types of bonds. So we should understand at this point that ionic bonds are metals and nonmetals, and they involve a transfer of electrons, and we're forming ionic compounds. Covalent bonds, again, covalent, sharing valence, are between two nonmetals because both nonmetals are trying to gain electrons. So they basically overlap their shells and kind of complete their outer shell, if you will. We call covalent compounds molecular compounds, ionic compounds, obviously ionic compounds. Now, why do we need to know the bonding? Well, because the different types of bonds will dictate how something dissolves and what happens when it dissolves, like how that substance changes when it goes into a solution. And we get this special word called dissociation. And that is where a substance, usually an ionic compound, will dissociate or break up into ions. So the key here is that we're forming ions, not just atoms, ions, charged atoms. So you can see here if you have sodium and chloride, so NaCl, you have sodium ions and chloride ions that are arranged in a sort of crystal structure. The water is actually taking apart the sodium and the chloride ions as ions, not as atoms. So they have a charge. We're going to be very picky about including charges on our ions in grade 12 because there's a big difference between sodium metal and a sodium ion. Now, remember that the solute is what is being dissolved, so it's what's going into the solution, and the solvent is what is doing the dissolving. So if we're talking about a solute, and last year we talked about the energy goes in, we have to break apart those solutes, like expand them apart. We have to break apart the solvents, we have to expand them out, and what ends up happening is you get your solution forming new attractions between them. Now, our solvent is what does the dissolving, and that's what we just said. Now, when we dissolve a molecular compound or a covalent compound, they dissolve as a whole uncharged molecule. And again, this is why we don't have sugar and such substances becoming electrolytes, because there's no ions floating around. There's a very big difference in terms of how an ionic compound and a covalent compound dissolve. So if we want to see what that would look like for dissolving a covalent compound, it looks something like this. As you see the water coming into the solute, it's attacking the solute from the outside in, so the outside gets dissolved first, but the water molecules are taking away the entire sugar molecule all at once. Not separating the molecules into parts of the molecules, it's taking the entire molecule as a whole uncharged molecule. So the compound's actually not changing, it's not being broken down or anything, it's staying together, just the actual molecules are separating. Now, if we go back to our lesson, though, when we look at ionic compounds and we dissolve them, things are a little bit different. So when we dissolve an ionic compound, it's going to look more like this. Now, macroscopically, it looks identical. You have a white solid going into clear colorless liquid, but microscopically, at the atomic level, we're actually taking the ions apart. And what you should notice is that the oxygen side is grabbing onto the sodiums, and the hydrogen side is grabbing onto the chlorides, except for this guy here, because that's a mistake in the applet here. But the hydrogen side of water is partially positively charged because of the polarity, electronegativity difference we talked about last year. And the negative side, the oxygen side, is slightly negative because of electronegativity difference. So there's attractions between the cations and the anions and the ionic salt. And the key here is what you get are ions in the solution. Oops. Brings us to a gentleman by the name of Savante Arrhenius, who is credited with this theory of electrolytes. And basically, he said that this idea explains how different compounds dissolve. Some solutions were able to conduct electricity because they form ions, and some do not because they don't form ions. He also figured out that certain substances can form different amounts of ions. So some can form like completely dissociate, every molecule breaks apart into ions, and some of them they don't. And that gives you different levels of conductivity. In other words, some are strong electrolytes or weak electrolytes, and we'll get into that a little bit more. Now, I can't remember which. No, this is not the correct animation, so we'll just skip ahead. So now, and we were very careful in grade 11 when we talked about concentrated and dilute solutions, not to use the terms strong and weak. And the reason for that is the words strong and weak imply how much something actually dissociates. So if we're talking about something like a polar covalent molecule like vinegar, it doesn't dissociate completely. It actually only breaks apart partially. So if I click on this, we should be able to see what vinegar looks like when it dissociates. So here we go. Here's a weak acid. You'll see it's HHA, and let's see how many of these molecules dissociate. Oh, only a couple did. The rest of them stayed as H and HA. So I'll replay that one more time. So you'll see of all those molecules that are going into the water, only a couple are dissociating. So vinegar is an example of a weak acid because it doesn't dissociate very much. It does dissociate, but not completely. Now, a strong electrolyte is something that dissociates really, really completely. So salt, NaCl, hydrochloric acid, HCl. These are strong electrolytes. Also, think of strong acids and bases. It's a strong acid because it dissociates completely. So let's see what that looks like as an acid. So here's hydrochloric acid, HCl. When we dump this into water, watch how many of them ionize. All of them did, which means that you're going to get a lot more hydrogen ions in the solution, which means that it's a stronger acid. It would taste more sour, react with your skin more, react with water more, all those kinds of things. So it makes it a stronger acid. So strength is talking about how much something dissociates, whereas concentration is how much is dissolved. We'll get into that more in the acid-base section. Now, a non-electrolyte would be something like sugar, where it doesn't dissociate. It stays together as a whole molecule, and that's what we were showing earlier, where the sugar molecule doesn't dissociate. It separates as a whole molecule. So if we were to write dissociation reactions for these, this is what it would look like. So let's start off with a non-electrolyte. So a non-electrolyte, something like sugar, so this is like the one that was in our animation. If this doesn't dissociate, it stays together as an entire molecule. So what you'll get is C11H22O11 just in aqueous. It's just in solution. So you're not forming any ions, you're not doing, it's just the same molecule just in water now. Remember, aqueous means in water. It doesn't mean liquid. It means it's dissolved in solution. Now, if we have a strong electrolyte, MgCl2 is going to dissociate into magnesiums and chlorides, but ions. So magnesium ion, which is Mg2+, aqueous, and it's going to make two chlorides. Notice I'm not writing Cl2, because if you think of MgCl2, when I break this apart, it's going to make an Mg2+ and a Cl- and a Cl-. We're making two Cl-, not Cl2-. Very, very important distinction there. If you write it like this, you're implying that the chlorides are bonded together, when in fact they are just ions floating around. Now, a weak electrolyte is the same idea as a strong electrolyte. The only difference is it doesn't completely dissociate, and you get this double arrow thing. So if I break apart aluminum hydroxide, I'm going to get an aluminum ion. Fix that. Aluminum ion, Al3+, aqueous. And we're going to make 3 OHs. So I'm going to put 3 OH- ions, like so. So we're getting aluminum ions and hydroxide ions, but we have this double arrow to indicate that it's not just completely dissociating, it's actually kind of resting somewhere in between. It's forming an equilibrium that we will get to later on down the road. So more on that double arrow later. So for right now, I'm not going to ask you to differentiate between strong electrolytes and weak electrolytes. I'm just going to ask you if it's an ionic compound, we break it apart. If it's covalent, we do not. Okay, that's basically what I'm looking for. So we should be able to write a dissociation reaction, and then from there we can actually figure out how many moles per liter of things we're going to be actually producing of the ions, and we're gonna do that right now. So it says write the dissociation equation and determine the concentration of hydrogen ions in a 0.5 molar solution of hydrochloric acid. So first things first, we're going to write down what hydrochloric acid is, which is HCl. So just need to get my thing working here. So let's try this. HCl. And when we dissolve HCl, we're going to make H plus ions and Cl minus ions. Now, if I'm going to include states, hydrochloric acid, it's not a Q. It's actually a gas. So this should be a G. And this should be AQ, AQ. So now what we're going to do is we're going to start with our, I'm going to fix this because that's pretty messy. Let's try that again. So we'll put a G there. All right, so now what we're going to do is we're going to start with our amount of HCl that we have. So this is 0.5 moles per liter. Now, I lied a little bit last year when we said we can only do stoichiometry in terms of moles. We can actually do it in moles per liter too. And the reason for that is if I have 0.5 moles in a liter of HCl, in that same liter, it should still be a 1-to-1 ratio for the moles. So that means that this is going to be 0.5 moles per liter. So there's your concentration of hydrogen ions in this solution. And this is how we can write it. Last year we talked about square brackets. Square brackets H plus means the concentration of H plus equals 0.5 moles per liter. Right? And that's how we would write our dissociation reaction and then find the amount of ions. Okay, now here's one for you to try. Give it a shot, see if you can figure it out. Pause the video, try it, and then you can check. I'll do the example right away here. So in this one, we're dissolving AlCl3. So if we're not told otherwise, I'm just going to assume it's a solid. I just knew that hydrochloric acid was a gas in the previous one. So, but if you don't know, just assume it's a solid. It's just easier. All right, so we know we're going to make Al3 plus ions, and these are going to be aqueous. And we're going to make 3 Cl minus ions, and these are going to be aqueous as well. So now, if we go and back to the question, they gave us 0.3 moles per liter of this. So we want to know the chloride ion concentration. Well, if I have 0.3 moles in a liter of AlCl3, we know that it's a 1-to-3 ratio. So to get from AlCl3 to Cl, I'm just going to have to times by 3. So my moles per liter here would have to be 0.9 moles per liter, because every time one AlCl3 dissociates, I get 3 chloride ions. So the concentration of chlorides is 3 times as much. So by writing a balanced dissociation reaction, we can now predict the number of ions that are going to be in the solution, the concentration of those ions. So these are little skills that we'll be relying on later on down the road, but in your work package, there should be a practice sheet on writing dissociation reactions, determining the concentration of ions and such.